Okay, so last set of examples is using, what if you were using a power model, like for example, in our fish situation where we used a cubic root. So that's a power of a third. So if you have a model that will fit a power model pattern like the cubic root, then you could use a logarithm on both the x and the y variables, and that should produce a linear pattern as well. I just want to quickly show you with the fish example. I've already got it in my calculator, so just want to quickly show you that with that example, if I go into here into stat and I say edit, and I've already taken the natural log of the fish here, of their length, and the natural log of the fish weights. And if I do a stat calc, so I'm going to do the linear regression. And I'm doing that with my natural log of x is in L3, the natural log of y is in L4, and if I even store the equation in vars, y variables, y1, oops, I think I didn't do that right, but do that again. Okay, store the equation in vars, y vars function, y1, boom, calculate it. And then, so you can see actually it's even a slightly better R value when you do your equation with logarithms on both axes. And if I go into the stat plot where I have L3 and L4 in there and zoom 9, you can see that it makes a very nice straight graph. So then the practicality, the reason why somebody might have used the cubic model instead of the natural log on both the x and the y is just because if you're having people on the boat finding the weight of the fish, maybe they're going to have trouble working with logarithms, but they would have an easy time just raising something to the third, to the cube power. So that's pretty much why. But like basically you can pretty much on any equation, if you're doing a transformation, try the log on one axis with the other axis not transformed, or try the logarithm on both axes, and probably a power model, that'll be something that might work. Here with data with distance from the sun in astronomical units AU and the period of 9 known planets, although I don't know if Pluto's still a planet, but so we can see that we've got distances that are going to be quite large as they're increasing quite rapidly in both of these directions. And that is something that tells me that maybe the log on both of the lists would be something appropriate. Now, that's what I'm going to do. So I would go into my calculator. And so to go into this here calculator and turn it on, and I've got my lists. So in L3, I'm going to put, I'm going to use the natural log again of the L1 list and the natural log on my L2 list. And so now my transformed x is in L3 and my transformed y is in L4. And I'm going to go into stat, calc, linear regression with those two lists, and I will store the equation just because I can in the vars function L1. And so calculate that. And that gives me an extremely nice R value of 0.9999. I don't even know how many nines that is, but there's a lot of nines. At some point, 1, 2, 3, 4, 5, 6, I think I got it. One more, 8, 9, 9. Okay, and so there's my equation for that. So then if I write the equation, I'll go and write it on the, here. Okay, so my equation is, okay, natural log of y is predicting, and then I've got my y-intercept of 2.54444 times 10 to the negative 4, and then it was a plus, now my slope, 1.49986, and then x, where y is equal to the distance from sun in AUs, which I can tell how AUs are calculated based on that. And X is my, what was X? It's the period of revolution in Earth years. In Earth years. Okay, so there's my equation. And so then if I want to use this model to make a prediction, what I want to do now is I want to use this model that I just came up with using natural logs, and I want to make a prediction. I want to make a prediction for a new potential planet that's out past Pluto. It's at a distance of 9.5 billion miles from the sun, and we're wondering if this new astronomical body could be a new planet. So we want to determine the period of revolution for this potential planet. And so the first thing is, because we know that here this distance had to be in AU units, we have to turn its distance from the sun into AU units. And so we take the distance for the Eris planet and we divide it by the distance for the Earth from the sun. And that results in our AU units. So that's going to be our input into the model. So now we're going to put this into the model. And so let's do that. So natural log of the period will be 0.002544 plus 1.49986. Now I'm going to put in the distance, the natural log of those AU units of 102.15. And then I'm going to plug that in. So natural log of the period. And if I plug in, please try it out, plug in the right side. When you plug that in successfully with the natural log in the right place, you get 6.939 ... roughly. So now I want to solve for the period. So I will have to raise both sides with a base of e. So that means that natural log can cancel with the base of e, leaving me with the predicted period. And that will be, and if I plug that into the calculator, e raised to the 6.939, I get 1,032, so 1032 Earth years, which we probably don't want to hang around to see if that prediction is good. But anyway, so there's our prediction. Now this, of course, is outside of our data. This is going to be extrapolation. So we know that it is definitely going to be problematic, but we can look at the residual plot. We can look at what happens with the standard error of the residuals. So like on average, our prediction error, we can look at those things to make a conclusion on if we feel like our prediction will be high, do we feel like it'll be low, or do we feel like maybe it'll be just right? Because in a situation like this, we don't have data for things further away. We can't wait and see if the period for this planet is really working. But before I go and look at Liner and look at all the things that are going to help us make a decision on if we feel like this is a good prediction, I want to show you a power model, which will convert what we have as a natural log model. It'll convert it into this form. And so let's go to the calculator and run that. Okay, so here's my calculator. Just to remind you what my R value was before. So if I go stat, calc, and go past the natural log regression and the exponential regression, you'll see power regression. So I will press that, and I'm going to do this time with the L1 and the L2 list, because if you're doing a power regression, the calculator is going to do the logarithmic transformations for you. You need to be working with the original data right here. So if you suspected something was going to be a power model where some kind of base was going to help you transform it on both axes, then you could always run a power regression and see how it works out for, I'm going to, I don't need to start, say calculate. And so as you can see, I get the same R value because the calculator is actually doing the transformation in its little calculator brain. But the format of a power regression is slightly different than an exponential regression, because a power regression, it has the X is going to be the base, and it's going to have a power on it, instead of like where in an exponential regression, your X is your exponent. So let's write this formula. Y is equal to, the predicted Y is going to be 1.000254477. And then my base is an X, and it's raised to the exponent of 1.49986. That's probably good enough. And then if I were to put into this model in this format, if I were to put the 102.15, that's the AU units for this new planet, potential planet, then my output of this, when I punch this in correctly, raising it to this right there, I would get 1,032 Earth years as my answer. So it already has done all the transformations involved in that for me. So, and that'd be appropriate to use that model too if you felt like you wanted, if you felt like it was a power model, that would be appropriate too. But being able to switch back and forth between the two versions, it's really important to be able to do that. Okay, so on to just checking all the liner for this. Okay, so I have to put the model back so that I will have the correct residuals. I need to calculate my linear regression back to the L3 and L4 lists. I think I will store my equation in vars, y vars function y1, calculate it. There's my nice model. Notice the R value. Okay, so now what we're going to check here is L. So to check L, I go into stat plot. I turn on my stat plot, scatter plot, and this is the wrong list because I really have it in L3 and L4. And so when I go there, I zoom 9, and well, that's not looking so good. It must have something else on. I'll turn this one off. Okay, so then zoom 9. And so that looks very straight. So first of all, that was a scatter plot. And I put the L4 on my y-axis and my L3 on my x-axis, and that looked straight, especially with the overlay of the nice equation on there. Then I'm going to do my residuals because, well, independent, I would say each planet's going to be independent of each other. 9 planets also is less than all the planets. 10% of all the planets, that's for sure. But n. Okay, so going to the residuals, and that's why I reran the equation, was because I wanted to be able to just pull the residuals up. So I got to do my histogram of the residuals. So second list gets me to my residual list. There's not very many points here. So, but I don't know. I'm going to look at the normal probability plot. I'm going to look at the box plot, but right now with only 9 points, I mean, how good can it really be? We're under 15. So let's go and try the box plot. You could really even just go right to that zoom 9. So there's my box plot, no outliers. Then I'm going to go into my normal probability plot on the residuals again. It's only 9 points, maybe a little, but, reasonably straight. Okay, reasonably straight. Normal prob plot. Okay. Well, let's put a Y on there. Okay. And then we want to look at the E. So we want to see if it's meeting equivariance. So to look at that, why don't we go into the stat plot, and we're going to go to a scatter plot of the residuals. So that means we have to change our x to being our x, which is our L3 in this situation, and call in the list of residuals. And then we zoom 9. And there does appear to be a pattern here. So if you think of our model is the middle, on this end, the observed values, okay, remember how it is, observed minus predicted. If it's coming out positive, that means if you're equals a residual, okay, that means that if you're, oops, no outliers. Okay, if you're getting something like that, then that means that the observed is higher than the prediction. So that would mean on this side, your model is under predicting. Down here, it's over predicting. And then over here, you're under predicting again. We're doing a point that's way out here. So I think our model is, it looks like we are under predicting, so our model is probably under predicting. So, and this curve kind of tells us that we're going to be having something like that, because the model doesn't seem to, the residuals aren't showing that equivariant scatter. So there's definitely some kind of an issue with the prediction of our model. Wraps that up. We did the LINER. We looked at it. We saw that sometimes models aren't perfect, but they can still be pretty good tools for use in the real world.